Hello, everyone, and welcome to Pivot 2022. This panel is Converting Coal Plants to Geothermal on the Horizon or Science Fiction. My name is Alex Fitzsimmons, the Senior Director with ClearPath. ClearPath's mission is to develop policies that can accelerate breakthrough innovations in the clean energy sector. So really happy to be moderating this panel. We have a great slate of panelists here. I think this is an incredibly timely topic, given all of the enthusiasm that we're seeing recently for geothermal technologies as a long-term clean energy solution. I mean, as you see traditional baseload power plants come under threat of closure, we still need to figure out how to maintain an affordable, reliable, and clean energy system. All of those three things need to work together in tandem, and very few energy resources can check all three of those boxes the way that geothermal can. And so that's why this topic is so timely. But I want to be clear from the outset that we are in no way advocating for the mandatory shutdown of coal plants or the conversion to geothermal. In fact, for this conversion process to work in the long run, it needs to be cost competitive without subsidies. And so that's the subject of our conversation today, whether coal to geothermal conversion is a realistic option for our clean energy future. And that's why we have such a great panel to talk about that today. I'll let them introduce themselves. We have representatives from CPS Energy, from the University of Texas, from Quaise Energy, and from Mackenzie. So I'm really happy to be moderating this panel with such experts. And I'll ask each of the panelists to just briefly introduce themselves for 1 minute or less, and then we'll dive straight into it. So with that, John, would you like to get going?
Yes, sir. Good day, everyone. I'm John Kosub, Senior Director of Energy Portfolio Analytics with CPS Energy. We're a municipally owned utility located in San Antonio. We basically serve the San Antonio, Texas service territory. One of my teams handles resource planning, so all the investment analysis for new plants, and we manage some R&D programs, some collaborative R&D programs. And that's it for me. I'll turn it back to you.
All right, thanks, John. Over to Ken.
Hi, I'm Ken Wisian, Associate Director of the Bureau of Economic Geology at the University of Texas at Austin. We are an applied geology and geophysics research organization, the oldest part of research at the University of Texas. I'm a geothermal geophysicist. That was my PhD work. I've been in the field since the 90s. Although if you saw my headshot, my career's been interlaced with the military. I'm also a retired two-star general. Our focus here is on resource assessment and site characterization, and it's definitely been picking up lately. Thank you.
All right, thanks, Ken. Let's go to Kevin next. No, we can't hear your audio, Kevin. Not quite. All right, we'll come back to you, Kevin. Let's go to Neeraj with WoodMac.
Thanks, Alex. Hello, everybody. My name is Neeraj Nandurdikar. I'm a Senior Vice President at Mackenzie, where I run our consulting practice focused on power, renewables, as well as energy transition and a variety of other sectors. But focused mostly, as what Mackenzie does, on market sizing, market opportunity, commercial opportunity, with a lot of focus on the commercial opportunity presented in the energy transition space, both for power renewables as well as various other technologies. So pleasure to be here. It's timely. Just in the last 2 years, we've had so many different geothermal companies trying to enter the energy transition space. So certainly exciting space. I've spent 22 years in the energy sector across various dimensions. So pleasure to be here. Back to you, Alex.
All right, thank you, Neeraj. Let's go back to Kevin, see if you're back with us. Not quite. All right, maybe we can get some help for Kevin, but let's just dive straight into it then. I want to talk about take a step back and look at the macro story here. the U.S. has had a huge legacy of coal power in the United States. It's been declining over the years. There's still a significant amount of coal power, both in the U.S., but especially globally. And coal is still growing in many parts of the world that are trying to produce more energy, to power a growing population and middle class, but they're all trying to do it in cleaner ways. So as we try to frame this this macro story about the potential to convert coal to geothermal, Neeraj, I want to turn to you to give a little sense of the market, the size of the opportunity. I mean, just how many coal-fired plants are there in the world? Where are they located? What do the macro trends look like here?
Yeah, sure. Happy to do that. First, I mean, we need to sort of think about when we say opportunity or the size of the opportunity, there's sort of a couple of different ways to think about it, right? One is obviously the number of coal assets, right? Just pure infrastructure, how many are there around the world? But the other way to also look at the opportunity is actually the economic opportunity and the incentives, whether these plants and owners of the assets actually have the economic opportunity to go through the conversions or what have you, right? But let's just start with just pure numbers perspective. What is the opportunity like? So at Wood Mackenzie, we track every single asset across various technologies, right? So our latest count shows that there's about 4,200, give or take, plants around the world, right? Of which about 3,200, 3,500 are what we consider operational. So they are working in some capacity, whether 100% or reduced capacity, but they're operational. There's about 1,000 plants globally that appear to be retired. They're either retired and decommissioned, or they're just retired, but not fully at the end of their depreciated life, if you will. And there's about 130, 150 plants that we consider as inactive. So that's sort of the global picture, right? So you're looking at more than 4,000 assets globally. Now, where are they? Now, probably not a surprise to anybody in the audience here, right? So number one, China. China has about 2,200 plants, of which about 2,000 are what we consider operational. Large capacity, almost 1 million megawatts of operational coal capacity. What's interesting, though, more than just those numbers, there's almost about 28, 30,000 megawatts under construction that we're tracking in China, and about another 30,000, 35,000 that are under development, right? So 84 plants that are under various stages of development. So that's one country where we actually see a increasing trend towards coal plants, maybe peaking around 2027, 2028 or thereabouts, right? So that's number one. Number two, US. US, we track about 740, 750 coal plants. Now, in some cases, by the way, I should clarify, there's also a little bit of a combined cycle, so some of them may have a natural gas element to them, but primarily these are coal plants. About 100 or so operating. Interestingly, there's about 500, give or take, plants in the US that we're tracking under retired category, right? So they're either reached the end of their physical life, or they've reached the end of their sort of depreciated life, or in some cases, the prices are down in their region that they can't make money either for energy prices or capacity prices, and they're just not working. About 200,000, 250,000 megawatt of operational capacity. Important point: no new projects under construction that we are tracking in the US. The third big one, India. About 200 plants, 30 or so retired. Another place where almost 7,300 megawatts are under construction, 10 or so actual units and plants under construction, right? So another country, increasing trend, 27, 28 or so, we see a peaking. And then you get down into other countries, right? So think about China, US, India, then you've got Indonesia, and then you've got Germany, right, at about 100. So Germany is about 115 plants. And after Germany, there's a long list of countries, which you're talking about 10, 15, plants. So, that's the big top 5 countries. And the opportunity is big, right? So in the US, if you just focus on US, a lot of states have RPS standards. And in many places, because of penetration of renewables, some of these projects aren't making the economic rent that they need, either because there's no capacity market, so they're not getting enough call to pay for energy prices, and there's not enough capacity revenue to keep them operational. So several projects we have seen either idle, shut down because of the economic or lack of economic incentive, right? So I think the opportunity is pretty significant when you have existing assets that haven't been fully depreciated. So I'll pause there and hand it back to you, Alex. But from our vantage point, the opportunity is big if something can be done with these assets.
Okay, yeah, that's really helpful. Thank you. That perspective on the size of the opportunity where these assets are, I think, is really helpful and will help frame the rest of the discussion. I think something else that will help frame this conversation as we go forward is Pivot has a short video, as a short intro video that I think will be useful for framing the rest of this conversation in terms of the market opportunity and the technological opportunity. So let's play that now.
There are more than 2,000 coal-burning power plants operating globally, with China, India, and the United States leading the world in coal-derived electricity production. Compared to other energy sources, coal-fired power plants have high carbon emission intensities, emitting far more greenhouse gases per unit of electricity generated. But they also produce large amounts of baseload energy within a relatively small surface footprint, with the largest producing more than 6 gigawatts of electricity. This high energy output presents a conundrum in envisioning how we might transition these plants into clean energy producers. Geothermal, and in particular, high energy intensity geothermal, referred to as superhot systems, may provide an avenue to pivot coal plants to produce clean, renewable electricity while largely utilizing the same footprint, grid connections, plant workforce, and plant equipment. So, what do we need technologically to enable economically feasible coal plant conversion to geothermal? Who are the entities considering conversion? What projects are on the horizon? And how fast can we go to convert coal plants to geothermal globally? Let's explore.
All right, welcome back, everyone. Hopefully that video helped frame the rest of our conversation. We're just going to keep rolling here. It's one thing to talk about the technical potential, right? So you can look at all of the assets around the world, but not all of them will be ideally suited for geothermal, right? So we want to bring in Ken here, who has a lot of technological expertise on geothermal, as he said, has been working on these issues for a long time. So Ken, based on what Neeraj was talking about, the market potential, how do you see geology having an impact here? How does the geology or the heat gradients overlay with Neeraj's commentary on where many of these plants are located? And can you speak to what specific geologic knowns or unknowns there are here?
It depends, Alex. Back to you. No, obviously the plants are worldwide. Even in the US, they're covering every imaginable geologic situation you can have, from very hot, tectonically active zones with volcanoes nearby to fairly cold, stable craton systems. So you have a huge range of thermal settings, a huge range of rock types, and what the rock column throughout the site may look like. So really, what I'd say is you combine Neeraj's economic factors, the demand factors, and all those other non-geologic things, the sunk infrastructure, how accessible it is, with at least a reconnaissance level assessment of all these sites so that you have some standard of comparison for looking at them. So what is the basic heat flow? What's the basic rock type? How big a surface area do you have to work with? What's the physical plant size? Because that's going to determine the sweep of heat that you can mine from underground. And then also another fundamental break point will be, is it more suitable for conventional geothermal, hydrothermal generation, or for the geothermal anywhere closed loop settings? What about, as we just heard previously, the super deep, super hot options also, or maybe a combination thereof? So there's all those things I think you need to look at some sort of standardized area, rack and stack them in priority order, and then start your deeper dive reconnaissance. Thing that we hear in this conference, and it's been great so far, the engineering is really sexy, but you can't ignore the geology. Egbert Joly in one of the earlier sessions was talking about that in a substantial way. Just like no matter how great a new jet you have, if you're going somewhere, you need as detailed a forecast of the weather at your landing site as possible. You still need that detailed geology knowledge. So, combination of the temperatures versus the rock types at different depths so that you know at my target temperature, I will be in this type of rock because that's going to affect everything else. And what you have to drill through. What are the reservoir, do you drill through aquifers, those kinds of things. So there's all that basic old-fashioned geologic detective work that's so common to, say, the oil and gas industry now. And I'm interested in actually transitioning that methodology and mindset into particularly the geothermal anywhere. The conventional hydrothermal, it has fairly well-established procedures.
So then, Ken, thank you for that. Based on your research and expertise, where do you think the most promising areas are going to be for this conversion?
Well, the hotter the better. So there was a paper published back in 2013 by Susan Petty at Alterrock that did an initial look at U.S. plants, and particularly in the conventional geothermal zone in the Western U.S., where essentially you've got plants that are at or very close to producing geothermal zones. So you have known high temperatures. You can step out from a fairly known condition and go there. So around the world, probably the tectonically active zones, the Ring of Fire and such, are probably your best bet for a near-term replacement for coal power. Getting to the level of energy density of a coal power plant is going to be difficult for geothermal. You might not replace 500 megawatts of coal with 500 megawatts of geothermal unless you get to those super deep, supercritical situations. But in general, the hotter the better at lower temperatures is going to be your lowest hanging fruit.
Okay, great. Thank you. Want to bring in Kevin now. Kevin, can you give a brief introduction and then maybe also provide a brief overview of Quaise and the technology and how you think it fits in here?
Thanks, Alex. Can you hear me okay now?
Yeah, we got you loud and clear.
Okay, great. Yeah, sorry about that earlier technical problem. So I'm Kevin Bonebrake. I'm the Chief Financial Officer of Quaise Energy. And I also head up our business development and technology commercialization. So I started as a mechanical engineer in my career and then spent a long time in energy investment banking. So I kind of look at things both from the technical perspective and also the economic perspective, getting to what Ken was talking about, energy density. So what is Quaise? So Quaise is a company that was spun out of MIT that is currently focused on developing a new drilling technology that utilizes high power, high frequency microwaves in order to dielectrically vaporize rock. So what does that enable you to do? It enables you to get deeper and hotter than anybody has been able to go before. And so why is that important? So to what Ken was talking about, that should enable us to get to conditions underground where we can reach supercritical water from a pressure and temperature perspective. So high enthalpy, high density, low viscosity. Those three things combined results in 5 to 10 times the energy density of conventional geothermal. And so when you think about taking that energy density and dividing it by the cost to develop a field, you see a step change in economics to geothermal. We think that per joule produced, we're going to be 5 to 10 times better than historical technologies. And then also when you're talking about that low viscosity and the mass transport part of it, our wells are going to be generating power on an order of magnitude of greater than 10x for a similar wellbore diameter.
Okay, great. Thank you for that. Yes. So can you talk a little bit more about, I work in federal policy here in DC, and one of the things that resonates in policy communities, especially with lawmakers and members of Congress, are jobs, right? So can you talk a little bit about what's from your perspective, Kevin, what sort of job creation, regional economic opportunities you think can be provided to some of these communities, if your technology takes off and you're able to do some of these conversions?
Yeah, sure. So as Neeraj alluded to, this is a massive opportunity. So we're quite simply talking about retrofitting all the coal plants on the planet, and then also greenfield development in order to supply clean baseload electricity to the entire planet. So traditionally, you would develop a geothermal field, and because of the energy challenges inherent to that, you would have to build a power plant and a turbine that is suited to the steam. We're flipping that on its head. We are producing steam that's of a pressure and temperature that we can fit it to the existing coal infrastructure. So just in terms of the volume of the number of plants that we would be retrofitting, so there's 250 gigawatts, of power generation just in the US. And we would need to drill what we call triplets. So that's one injector and 2 producers, and each of those generates about 70 to 100 megawatts each. And when you run the math on the number of rig hands we would need just to develop those geothermal fields, I think that if you assume we're retrofitting coal plants in the US between 2030 and 2050, just the retrofit, just the drilling alone, we would need 6,000 rig hands in the US. And if you rolled that out to the rest of the world, where you have about 8 times the coal capacity, you're talking about something more like 50,000 hands. And then when you factor in greenfield development and also the support staff, I think we're talking about something on the order of magnitude of like 15,000 people in the US and 120,000 globally, which is about the size of, for instance, Schlumberger or Exxon's workforces. And that's just the drilling aspects. So we would also have to manufacture the rigs that are associated with this. And I think we would need a fleet of about 200 to 400 rigs in the US and 8 times that internationally in order to deploy over 20 years. And then the amount of tubular that would be involved in developing all these geothermal fields around the world would be massive as well. So we think that there would be significant job creation and significant economic benefits. And importantly, we would be able to take advantage of the existing oil and gas workforce and completely pivot it to this purpose for at least 20 years or more.
And Kevin, I think that last point you made is particularly important. Not all clean energy jobs are created equal, right? And a lot of these jobs in the oil and gas sector in particular are highly educated, high-paying jobs. And so when you're talking about converting to cleaner energy resources potentially impacting communities, you have to be able to provide alternative job opportunities that match their skill set. And their salaries, right? And geothermal is one of the few clean energy technologies where you can credibly make that case, right?
That's right. And that's why we're so excited about it. So the majority of our employees are in Houston, and we have an oil and gas background. So our founder, actually, one of our 2 co-founders is an ex-oil and gas person. So we are keenly aware of that, and we're very excited about the opportunity.
Great. Okay. Want to get John in on this conversation. So John, you're with CPS from the utility perspective, I want to ask you, you've heard a lot about the macro opportunity, the technological opportunity. I mean, from your perspective, working for an energy company that might potentially invest in this type of project that already has a large fleet of plants in operation. I mean, how feasible is it to use geothermal to repower some of these coal plants, and how would you see a potential coal to geothermal conversion jiving with CPS's long-term clean energy goals?
Yeah, okay, thanks, Alex. Yeah, so coming from the end user perspective, zero emissions is good. We need zero emissions, load following, or controllable type resources, and bulk storage can help. Maybe small modular nuclear reactors, things like that. But geothermal, it's pretty exciting. We took a hard look about 2007, and it got very quiet. Now it's starting to kind of gear up again, and we're starting to hear some details on some exciting new technologies. Now, our utility is transitioning to cleaner resources, like many utilities. The city of San Antonio has a goal to be carbon neutral by 2050, like many cities. We have coal, nuclear, gas, renewable assets, solar, wind, battery storage, landfill gas. We have a diverse portfolio. This would be a nice addition. Now, as far as adding geothermal, kind of intrigued about what Kevin has to say, because it's he said hotter and deeper, and that's certainly what we're kind of thinking you have to do in the state of Texas. If you just kind of look at Texas, you got to go fairly deep with a well. 15,000 feet, about 300 degrees F. And, kind of given that, I'm kind of intrigued, and maybe we can hear more about this technology that could potentially provide the steam pressures and temperatures to, reuse some of the equipment we have. Now, converting coal plants to the geothermal, something I hadn't really thought about until this panel, but very intriguing. So, reusing these investments, these large investments we made for our customers, has some potential there. So reusing steam turbine, potentially the boiler, electric infrastructure, cooling water, the grid interconnection, all those things, have a pretty significant, cost advantage, and, and really reusing the workforce. You continue to use the workforce and use that at a shared site would be a big advantage too. Really, accelerating that research and development. How do we do that? How do we reduce the risk? We've heard a lot of pitches, but we're starting to hear some now that are starting to take shape. And how do we get to that proven and mature stage? How do we get some certainty in the operating and maintenance capability needed? What skill sets do we need? What sort of geologic support, from geologists, things like that? And then these are going to be billion-dollar investments. So how do we do that in a manner that is kind of sequential, and we kind of get there and kind of maintain our kind of risk profile.
All right, thanks, John. Kevin, I want to ask you a follow-up here. So you heard John say that these ideas are intriguing. It's becoming more reality than it maybe was in the past. What would your pitch be to people like John who are intrigued by the potential here?
Right. So the thrust of my pitch, Alex, is that this is not new technology. This is a new application of an existing technology. So what I mean by that is the devices that we are using at Quaise in order to generate microwaves, as I said, to dielectrically excite rock in order to vaporize it, is existing technology that was developed actually in the 1960s and was first started to be used in the 1970s in plasma heating for fusion experiments. So this exact technology and most of the components have been used to heat plasma to 100 million degrees Celsius in fusion experiments. What we're doing is we are turning it towards the ground and heating rock. It's just the application of that technology, because we are not in a clean fusion lab. that's been baked to a vacuum with gold-plated devices. We're actually going to put these devices on land rigs and take them out in the field and develop geothermal fields. So it's a new application of an existing technology.
Alex, can I chime in on that?
Of course.
Okay. Earlier I talked about prioritizing the tectonically active areas, but also, although you wouldn't get as much energy density out of it, there are multiple companies, which we'll hear from, I'm sure, during this conference, that are working on medium and low temperature geothermal anywhere systems. And if you've got a plant that's already shut down, it's just sitting there, there's nothing wrong with looking at a phased approach where you start generating with technology that's essentially in demonstration proof of concept phase now, and add to it as deeper, hotter technologies or other supporting technologies come online. So for the utilities, I would say that the technology is there right about now. It is coming online in the proof of concept phases. So you will see a lot of clarification, I think, over the next year or two, as more of these ideas, everybody has great models, but as more of them prove out. Thanks.
All right, great. Thanks, Ken. Yeah, so we're getting a lot of good questions in. Want to make sure we leave plenty of time for questions from the audience. So please keep submitting your questions here. I want to address one. A couple of different versions of this question have come in here, basically to the effect of regarding the comment I made about the beginning about being geothermal being cost competitive without subsidies. Is your argument that coal, oil, and gas have not been operating with support and subsidies? That's one version of the question. And why must geothermal need to develop without subsidies when coal, oil, and gas have received them forever? So I think it's important to note that yes, all forms of energy have received some version of subsidies in the past, whether direct mandates or grants or tax credits. And ClearPath works on a variety of market signals, market-based policies and incentives to try to create more clean energy. But I think ultimately, all of these technologies need to drive towards being cost competitive if they're going to work in the long run. I think the long-term goal is to make all of these clean energy technologies, including geothermal, cost competitive without subsidies. That doesn't mean they won't require some market incentives to get there, and geothermal should leverage those, and we should try to do those in as fiscally in as prudent a way as possible. But yes, I mean, all forms of energy have subsidies. But if a technology is going to be sustainable in the long run, it eventually needs to become cost competitive on its own. So that was the main point here, and that's ultimately that innovation, that R&D that you're hearing about here is ultimately what will drive the success or failure of coal to geothermal conversions more than any policy mechanism in the long run. So we're getting a lot of good questions in about the technology, some about the size of the market. So one question we have here is for John. Is CPS actually thinking about doing a coal plant conversion? What would be behind your thinking here? Is this near term, or maybe another way is, what would you need to see to make this feasible for you all to do?
Yeah, tough question, right? Because utilities tend to be very conservative when it comes to investments of this type. There is some potential to maybe use our site for some sort of a pilot project, potentially. We have 2 units that we closed early, 2 coal units. Those are 420 megawatt size steam turbines, so we would need to adequately match that turbine to the the energy type from the geothermal. We also have one up, the largest one is 785 megawatts, so very large scale. wondering if if that would, is that the right step? It sounds like maybe there's a smaller step, and maybe there's coal units tend to have large acreage, I guess some of the legacy coal units. So there may be some opportunity to use some of the property for pilot testing, things like that, scale it up, eventually get to, a commercial scale. So I'll throw that out there as some ideas. I know you mentioned, can we do it without subsidies? Those have been successful in some respects, but can you sustain with that? We have the Low Carbon Resources Initiative that's many players with the Electric Power Research Institute. So that's another method, a collaborative research method. Can that help accelerate? They're working on a lot of things. Geothermal, I think, can be one of those that can maybe help accelerate and get the fundamental understanding down and established, and then move into pilots, et cetera.
Okay, thanks, John. All right, this next one is probably for Ken or Kevin. Are coal plant conversions possible on a gigawatt to gigawatt scale, or will these plants be scaled down when converted to geothermal?
Well,
Yeah, I can take you, or go ahead, Ken.
I'll just start off on the low end of it. No, if you're talking medium to low resource temperatures, 250 C and below and such, unless you've got, as John was saying, a large surface area that you can harvest heat from, you're probably not going to do a one-for-one replacement. But again, you're still taking advantage of sunk infrastructure. And if your plant's producing zero right now, anything's an improvement.
Yep. And so sorry, Alex, should I follow up?
No, go ahead. Go ahead, please.
Yeah, so we have not modeled plant conversions that high, but we've modeled up to 350 megawatt plant conversions. And Ken is absolutely right in terms of the surface area that would be required if you're going down to, say, 200 degrees C, but we are envisioning going down to 400, 450, 500 degrees C temperatures. And then also we'd be getting to pressures that are in excess of 25 megapascals. So I was talking a bit earlier about the energy density. Our energy density is going to be 10 times as much for a given fluid flow. So that translates actually to needing, well, it's a little bit more complex than that, but it translates to needing a lot less surface area than a lower temperature field.
All right. So in that same vein, Kevin, a couple of questions for you about Quaise's technology. So I think you might have mentioned this, but what subsurface temperatures are you basing your use cases on? And then if you are vaporizing the rocks, which sounds like you are, do they solidify as the vapors move uphill? And how does one get the vaporized rocks out of the wellbore? Very technical questions.
Yeah, no, those are great questions. So in terms of what was the first component of the question, Alex?
Yeah, the first was what subsurface temperatures?
Oh yeah, okay, thank you. Yeah, so I mentioned earlier we are looking at using existing turbines and producing steam to meet those specifications in terms of a temperature, pressure, and mass transport perspective. So when we're looking at developments, the most economic is when we're looking at supercritical, which would be around 450 degrees Celsius plus. We've also been looking at what the economics would be if you produce subcritically, say at 350 degrees. In both of those cases, you're either getting more enthalpy or more density or both. And in the supercritical case, like I said, much lower viscosity, which is actually important at the bottom of the wellbore when you're talking about how easily that supercritical phase can flow from the injector to the producers relative to normal liquid water. And then the second question about the vaporization. So we are heating the rock to about 5,000 to 6,000 degrees Celsius at the bottom of the wellbore. And that rock vaporizes and turns to ash. I should also mention importantly, we're using conventional drilling to go through the sedimentary basin. And so what we're really talking about then is switching over to Quaise's millimeter wave drilling technology when you get to the basement. And that is primarily granite and basalt. So think about the ash that falls in a volcanic eruption. Right? We're vaporizing that rock down to its constituent molecules, and then we are flushing the system with an inert gas in order to carry that ash up and out of the wellbore. There is a melt zone, and that has to be carefully managed, but our preliminary indications are showing that we're going to be able to manage that. It's an excellent question to answer or to ask, though.
Okay, great. Thank you for that. Yeah, we're getting some other questions in here about the environmental risks, presumably the legacy risks, fly ash at these sites. How would you address heavy metals, seismicity issues with these sites? Any thoughts on that?
Yeah, so first of all, we're conventionally completing the well, including casing down to the basement, right? So the well should be fully isolated from aquifers and heavy metal and other contaminants like that. And then we are creating channels between the injectors and the producers. But again, this is going to be in granite and basalt. And then it's going to be a closed loop system in the sense that we are circulating water around and around, right? So when you think about seismicity, the vast majority of the seismic issues that have occurred in oil and gas drilling has actually been because of wastewater disposal, where you have massive volumes of water that are going into the well with nowhere to go, right? So it's going around in faults and it's causing slippage. With us, this is a contained system where it's going around and around, and then also the channels that the water is flowing through is down in the brittle ductile zone. So that is, we believe, much less prone to slippage than channels that would be in the sedimentary basin. And I'd invite the geophysicists on the panel to comment on that, because I think a lot of that is theoretical given the lack of actual real world tests that have been done at those depths.
Yeah, Ken, you have any thoughts on that?
Yeah, let me add to that. One of our other functions here at our organization is we run the induced seismicity network for Texas. So we've been closely monitoring oil and gas induced seismicity for a long time. And yes, most of it is from water disposal, although it does vary from basin to basin. In some basins, it is the fracking. As we've already heard here today, the thought is that geothermal drilling, stimulation, fracking, whatever, will be significantly less risk than the oil and gas. But honestly, we need to prove it. We need to be open and honest with the data. We have already instrumented and been collecting background information on one geothermal project site in Texas, and we monitored a recent geothermal test drill in Texas, and it had no recorded induced seismicity in it. But that's an issue environmentally. I think we as a industry need to be upfront about and push the information openly just to avoid the not in our backyard issues. One of our projects that the Air Force has funded that's in phase 2 design phase is inside the city limits of Houston, Texas. So obviously we're going to be pretty careful there.
Yeah. Hey, Ken, let me stick with you. One question that came in is there a need for a screening tool here with technical, financial, and regulatory aspects?
I'll throw that back to the whole panel, but the short answer is yes. You've got right now, you tend to have the geologic models. I know a couple of folks and organizations that are working on coupled geologic electricity models, throwing in the economics. LCOE has been talked about a couple of times, but that as a metric is a little limited, and there needs to be work even just on a broader thing than LCOE, that's life cycle analysis. But yes, a publicly accessible or shareable modeling tool that can help utilities and other folks assess comparing options would, I think, be a significant step forward.
Yeah, let me ask you the same question. Let me throw this over to Neeraj, with WoodMac. I mean, you work on this sort of thing. You've already done, like the macro analysis. Are you thinking about getting more granular than that to overlay that macro picture with with the financial and the technical info?
Yeah. Can you hear me okay, Alex? I lost power in the middle of all this.
I hear you great.
To our topic. Great. So yeah, we've in fact actually with Quaise, we've actually done one level of this already, which is focusing on the US. We've already done two things, right? We've already mapped all the coal plants in the US, and we've looked at their economic life, right? Where they are and whether they are going to be in the money or out of the money because of RPS standards, because of power prices in their territory, whatever the case may be. And on top of that, what we've actually done is working with Quaise, we've mapped the temperature pressure gradients across the entire US. We've layered the basement rock layers, the sedimentary rock layers. And because we also have an upstream research organization, we've applied our drilling knowledge and drilling rates and et cetera. And we've already created an integrated tool that combines the physical assets in US with a pinpointed assessment of, at that location, what is the geothermal attractiveness in terms of how deep you have to go for that temperature Kevin talked about, what is the layers of rock look like, how long will it take us? And ultimately, we have ranked the US coal plants in terms of attractiveness, both economically for them and geothermally, if you will, right? So we already created a matrix. Now, what's not fully done is the environmental aspect, although within each state in the US, we kind of know what the environmental stances are, but there's more to be done there, right? So 2/3 of the work in terms of a matrix is already done. But you're absolutely right. We're going to add that third layer of sort of environmental and sustainability to it. Great.
All right. Got some questions here about the costs of doing this. This is really for anyone. What does the math look like on the dollars per megawatt hour for the power generated by retrofit or repurpose coal, CapEx, OpEx?
I can take a shot. I'm probably the only one that has all the pieces on that one. And I'll preface this by saying, again, this is just specifically for our system at the energy densities that we're talking about. Okay, so I don't think you can generalize this across all geothermal developments. But we are looking at, so we think in terms of triplets. Okay, so we have an injector well, and then we have two producer wells. Those wells cost about $15 million each, we think, to drill and complete. And we think that they generate about 35 to 50 megawatts per producer. And so if you run the math out on say a 350 megawatt plant, we would need something like 5 of these triplets at $45 million each. So that's about $225 million. And then in order to prepare the surface area, it would be like another $25 million in order to install all the connections from the wellhead to the tailgate of the existing plant would probably be like another 75 to 100 million. So we get to a levelized cost of energy at about $20 per megawatt hour for a brownfield development. Greenfield, in terms of building the power plant on top of that, obviously it's going to be higher, but we think even with conservative assumptions on cost, you're going to get to something that is competitive with solar and wind.
All right, yeah, thanks, Kevin. John, so based on what you've heard from your perspective, are you any more or less convinced that that there's a role for coal to geothermal conversions in the future of your business?
Well, certainly got my attention with that number of $25 a megawatt hour. So certainly has potential, and we'll see how it goes.
So Ken, from your perspective, just have a couple minutes left here. What would be some positive signals over the next couple of years for you to see out of the industry to as signs of progress that this could, as the title of the panel said, move from science fiction to science fiction to being more than on the horizon and actually being being a real thing.
Actual projects is what I would say. Again, up until fairly recently, most of this is modeling. But a lot of these advances in drilling technology, we haven't gotten into it much here, but the conversion of heat to power technology, using new fluids like supercritical CO2, are all coming into that proof stage now, where you'll have physical proof that they work. So we are really, I would say, ready to launch if we can just bring together the right utility, the right contract and engineering expertise, and the right site to launch the proofs, to show that it can be done. And yes, the first wave will be on the more expensive side, but with development that will drop, as with any large industry scaling, and the scaling can be tremendous. Kevin's already talked about that. But when I look at scaling, what I think back to is the shale boom here in Texas, where at its peak we were drilling 15,000 wells a year in Texas. That's how fast you can scale up geothermal deployment once things are proven. So I look at it as we are right on the cusp now, and the picture could be accelerating dramatically over the next few years. We just need the proof projects to land now.
Well, I think that's a wonderful place to end it. Thank you all for this panel. It's been fantastic. Thank you to the audience for all the great questions. I mean, I think one of the reasons this is so promising, as I said at the beginning, is we all want an affordable, reliable, and clean energy system. There's very few technologies that can actually check all three of those boxes. Geothermal can. And so it's great to see all this enthusiasm for a cleaner energy future. Finally, geothermal starting to get some of the attention that it deserves, and we just have to keep pushing forward, and we can make great things happen. So thanks everyone for joining. It's been great, and we look forward to working with you to make geothermal more of a reality. Thanks everybody.
Thank you.
Thank you.
Thank you, Alex.